Alright guys, so we're going to continue talking about astrophysics here. Now this is one of the last things you did in your reading, is you were learning about the luminosity and how it depended on temperature. Now one of the things that I want you to notice is that when we look at these curves, okay, it doesn't matter whether we're looking at the purple curves or the yellow curves or the red ones, it doesn't matter which star we're looking at. When we have a black body, that black body, yes, absorbs all the radiation, but it's also a perfect emitter. Now, being a perfect emitter doesn't mean that it emits everything, but it does mean that it's going to emit luminosity times its the sigma times A times T to the fourth. So depending on the temperature, that's how luminous it will be. Now, what I want you to notice is that even though there is a max wavelength, right? There's a specific wavelength that's the most common or the most intense. It also covers every other wavelength, and it kind of looks like it ends here. It doesn't actually. It actually goes down and continues going. This end as well, right? The sun continues to emit all of those different wavelengths, right? And so we need to recognize that that's why when we look at stars, the stars look white, because it has all the colors, everything from 400 up to about 700, right? Those are our visible colors. Even these ones that are the purple, right? The high frequency light stars, they still have several wavelengths within the visible region. And because it's within the visible region, it's going to give us all the colors put together, which is going to look white. Though the majority of it will be on this purple or blue end, which is why the star may appear to be a little bit bluer. Same thing with the red ones, right? The red one is going to still have light all the way from here to here. It's still going to look white, but because there's more red than blue, it probably will have a little bit of a reddish tint, okay? Now remember that this area, okay, is the area, the surface area of our star. And so sometimes we can use 4 pi r squared, and that r is the radius of the star. And that's something that can kind of help us out as we're working through problems that have a star of a specific temperature or radius and creating ratios, right? Okay, I think that's probably enough on this. But again, I wanted to make sure that you understood that all of these different temperatures emit all the different frequencies. It's just a matter of which one has more of the higher frequency or lower wavelength as compared to the others. All right, let's move on to the next slide. Okay, this is what's happening inside the star. Okay, now this is an important idea because what's happening here is we're having hydrogens that are combining, right? As those hydrogens combine, then it gives us it combines in fusion. We then have a hydrogen, we lose an electron there so that we have now a neutron and a proton, right? So it's now a 2H combines with another hydrogen. Now I have 3 nucleons, right? 2 of them are hydrogens, 1 is a neutron, and so I have helium now, which then when we combine with another helium from a very similar process, the same process in fact, those 2 come in together. We lose 2 of those extra protons, leaving us then with 2 protons and 2 neutrons, which is our helium-4 atom, 2 protons, 2 neutrons. Recognizing that here, right, in this first step, right, when we have the 2 protons coming together, what do I have to lose here in order for me to end up with a proton and a neutron? Well, recognize that in order for this proton to turn into a neutron, it needs to lose its positive charge. So it's going to lose a positron. This is beta plus decay, right? We're losing a positron so that that proton can turn into a neutron during this process. All right. I got a question. Anybody know what Vega is? It's interesting. Not a lot of people know the star Vega, but it actually used to be the North Star. About 14,000 years ago, it was the North Star, not Polaris. Okay, now this depends on several things, the movement of the Earth, this position of the stars in the sky, I mean all those other things. It's actually not that far. It's about 25 light years away. which is still pretty far. 25 years is the speed of light for something to get here, but still, relatively, compared to most other stars, that's not all that far, 25 light years away. It's the first star that was photographed, lots of other things, but we don't talk about it too much. But I wanted to talk about Vega here because I'm going to show you something about Vega. How do we know anything about Vega, right? This star that is 25 light years away, took 25 years for the light to get. If Vega were to explode today, you wouldn't even know till you were more than 40 years old, right? That's how long it takes that light to get here, right? So given that that's the case, how do we know anything about Vega at all, right? Well, this is how. What do you remember about this? Hopefully you're starting to remember this was our absorption spectrum, right? We actually saw the opposite of this earlier. Okay, we saw something that was the emission spectrum. The emission spectra is when we had specific bright lines, right? We had some purple lines down here and blue lines, and we had some red lines up here. We looked at the gas tubes for a couple of different gases, and we saw those bright lines. So this is what's called an absorption spectrum. It's actually the opposite of that, right? When you have a gas, right? So you have something, let's say we've got our star here, which is putting out light in all different frequencies. If we have a gas that is surrounding that star, as this light passes through, that gas is going to absorb specific wavelengths of light. Just like when we excite that gas, it emits certain wavelengths, it's going to absorb those exact same wavelengths because those are the wavelengths that the electrons can jump around and absorb. It's going to absorb those wavelengths. Now, some of those wavelengths will be shot out in the same direction, but others will be shot in all other directions. And so when we look at the light from a star, here we are over here, what we see is not exactly the light being put out by the sun. We're going to see some lines that are missing, okay? These lines right here. These lines are missing because they were actually absorbed by the gas that is on the outside of the star. Now, because of that, because of the light on we can figure out what is the gas on the outside of the star, and therefore we can figure out some things about the star. Now, this is actually really, really neat. Okay, I want to show you the next little bit here. Okay, I want you to look at the absorption for Vega and the absorption for our sun, for the star. Our sun, which is also a star. Look very closely. The sun is down here, okay, and Vega is the purple one right above it. What are some things you see? Go ahead and pause it for a second and decide what are some of the things that you can see when you look at these two spectra. All right, so hopefully you've noticed a couple of things. Number one, hopefully you've noticed that Vega kind of goes up like this, right? Vega is a much brighter star. You can see that it has a much higher intensity. Looking at our intensity over here, much more intense than the sun. Okay, secondly, you'll notice that the peak hasn't actually happened yet. The peak's probably going to happen somewhere over here, right? When we're looking at my blackbody curve. So this Vega, okay, is going to be more of a bluish purple star, higher frequency at its peak, right? Whereas we already know the sun is kind of one of those yellow stars, and so we can see its peak somewhere around here, which is why we're getting a good variety of different colors. Okay, so hopefully that's one of the things that you're seeing in connection with what we did before. Now, something else I hope you're seeing is look at these. Look at the absorption spectra right here. Okay, that one right there. This right here, this dip, okay, these dips are specific places that the light from the outside of from the sun is getting absorbed by the gases that are in the photosphere of the sun. Now, this is what I was talking about in my previous slide, is that you've got a star or a sun on the outside surface of the star, right outside, is what's called the photosphere. I didn't give the name before. Okay, and the photosphere is gas that absorbs specific wavelengths. And you can see that Vega and our sun more or less are absorbing the same wavelengths there. Okay, now this is interesting because that means that we expect that Vega is undergoing basically the same process that our sun, because it has the same type of photosphere on the outside. Now, there are some slightly different things. We see some other things in here. That's because they are undergoing some slightly different things. But we can tell that there are some things. This hydrogen, this up here is the hydrogen spectrum. We can see that those absorptions line up perfectly with many of these that we see in our hydrogen absorption spectrum. All right? As we move to the next little slide, this is actually how stars used to be classified. Stars used to be classified based off of their color and their temperature, right? And by looking at the color and the temperature, they were classified, and very often that led to certain sizes and masses and other things. But the size and masses weren't nearly as important as this color and temperature were. Now, we don't really organize stars by that so much anymore. They still are, but this is going to be less important for you as an IB student. I just wanted to kind of point out that, you know, in these different colors, different wavelengths, we have different types of gases that we expect are being prominent because of the types of gases that are in that photosphere. All right? Now, we're going to move on, because one of the other parts of this idea is something called Wien's law. We've actually looked at Wien's law before, right? Wien's law basically says, well, if a black body has a very specific curve, right, this curve belongs to a specific temperature. And therefore, a specific temperature will have a very specific wavelength at its maximum. And that's what Wien's law says. Wien's law says that if I can measure the wavelength, the maximum wavelength that's showing up when I look at this star, I know what its temperature is. This is something that we've learned from observing black bodies on Earth. Now, our assumption, of course, is that the physics on Earth is equal to the physics everywhere else. We hope that's a good assumption, because that would make physics consistent everywhere. But I mean, it's difficult to say, obviously, from where we are here, since we can't actually see those things. That's one of the cool things about astrophysics, is that we're learning things about the universe around us by looking at the physics that we know here on Earth. And Wien's law, which we did cover during our core, is one of those things. This is one of those important ideas. Okay, so looking back at our picture of the sun in Vega, you can see here the maximum for the sun is somewhere around this 450, maybe 460 nanometers range. So we should be able to take that and put it into our wavelength here, and then we could calculate the approximate temperature of the sun. Okay, give it a try, see what you get. You should get something around 6,000 Kelvin. Don't forget to put this into meters. You've got meters and kelvins on the top. So here what we have is about 460 nanometers. Make sure to turn it into meters, work it out. Hopefully you get something around 6,000 Kelvin. Okay, now that'll depend on what you choose for this maximum temperature here, or wavelength here. You may choose about 450, 460, 470. Any of those should give you around the correct temperature of the Earth. Obviously, if we had a better way of measuring that maximum wavelength, then we'd get a more correct answer. All right. All right. Let's move on. One more thing. More things actually before we wrap this up. I want you to consider this question right here. I want you to pause the video in just a second when I tell you to. Read through the question, work through it as best you can, and then go ahead and play, because I'm going to pop the answers right up here. Ready? Pause the video. Kazam! There's your answers. Hopefully you got something like this, but I'll go ahead and go through it with you just to be sure. Okay, so first it wants to explain black body radiation. All right, so here's the keys. Okay, black body radiation is emitted by a perfect emitter for a given temperature, for a constant temperature, all right? It includes all wavelengths. This is what we were talking about at the very beginning of this video, right? That includes all wavelengths of electromagnetic waves, okay? So the blackbody radiation is what's being emitted by a perfect emitter for a given temperature, including all wavelengths, all right? So this right here, letter B, is an example of that, okay? Obviously, because of the curve, we know that the x-axis should be the wavelength, the y-axis is the intensity. The second question wants us to do, letter C, a star that has lower surface temperature and lower apparent brightness, okay? So a lower surface temperature, remember we're going back to Wein's law here. Wein's law is that the temperature is equal to 2.9 times 10 to the negative third over the maximum wavelength. By maximum wavelength, that's the one that's most common, okay? Now, if the temperature is lower, because it says a lower surface temperature, if we want temperature to be lower, what needs to be true about our maximum temperature? Well, in order for that to be a low number, this needs to be higher, okay? Secondly, it says lower apparent brightness. So if it's going to have a lower apparent brightness, that means it needs to have less intensity. And so you'll notice in my drawing here, this was the original maximum wavelength. The new maximum wavelength is a larger wavelength. It's over to the right. That larger wavelength is going to give us a lower temperature, okay? To show that it has a lower apparent brightness, we're going to have lower luminosity, which is why we have a curve that has much less area than the original, okay? Letter D, you can see here, we just put in the wavelength. Please remember to put it into meters, and that should allow you to calculate the temperature, which should be very close to 3,000 Kelvin, all right? One last thing before we not sure about this video and let you get to some problems. Let's work out a couple of other examples, okay? Look at each one of these three. I'm not going to read them out to you. You can read. Go ahead and read each one of these and see if you can work through it, okay? When I tell you to pause, please pause, because that'll give you some time to work through. And I'm going to go right into working them out and making sure that we can get the right answers, all right? Okay, give it a pause. All right, so hopefully it took a little bit of time there to work through this. So the first one, the radius of star A is 3 times that of star B, and its temperature is double that of B. So we got temperature and radius, and it's asking for the ratio of the luminosity. So this is the equation we're going to use. It wants the ratio of luminosity of A to B. So I'm going to put luminosity of A here, and then I'm going to put luminosity of B on the bottom, which means on the other side I'm going to need sigma 4 pi r squared over t to the fourth. The A's are all on the top, the B's are on the bottom. If you need to label those, then go ahead and do so. Okay, with that I should be able to cancel out those. I can cancel out the 4 pi's because those are unimportant. The radius of star A is 3 times that of star B, okay, which means that RA right here up on the top, this would, all right, so RA is 3 times RB, and then the temperature is double that of B. So TA is 2 times TB. Okay, so I'm actually going to recopy this here, which means that the luminosity of A over the luminosity of B is going to be equal to, so I've got the radius of A, which is 3 radius of B squared, times the temperature of A, which is 2 temperature of B to the 4th power, over radius squared of B and temperature of the 4th of B. Okay, remember the powers should distribute, okay, which is going to give me a 3 squared up on the top, so that's going to be an 8, and then 2 to the 4th power, which is 16, and then that'll have my radius of B squared, temperature of B to the 4th, which of course is going to cancel with the radius of B squared and the temperature of B to the 4th on the bottom. Therefore 8 times 16, or in other words 144 is my final answer. So the ratio of the luminosity of A to that of B is that it's 144 times larger. All right, very good. Sorry, that should be a 9. 9 times 16 is 144. There we go, much better. Sorry about that. Okay, now we'll look at the next one. The stars have the same apparent brightness when viewed from the Earth. Which is farther? How much farther? Okay, so now we're using this equation, B equals L over 4 pi d squared. Now this time we're going to be solving for d. We're going to get d by itself, so we're going to do some rearranging for it. First, I'm going to move the d squared over to the other side. So we're going to need that d squared is equal to L over 4 pi b. So I multiplied by the d squared, I divided by the b. Okay, then we can square root it or do it to the half power. You can just leave it for now, it doesn't matter too much. So again, I'm going to do I'm going to find a ratio of dA over dB, which then will put this over LA over 4 pi b. Sorry, this is LB, and apparent brightness of B. This is luminosity of A, apparent brightness of A. So the 4 pi's are going to cancel out. This is going to lead to dA over dB equals, now this is LA over BA, this is LB over BB. Instead of dividing, I'm going to multiply. So instead of dividing by LB over BB, I'm going to multiply by the reciprocal. So I'm going to have LA BB over BA LB. Now these numbers I have, the stars have the same apparent brightness, so these two go out. And then I already know that LA over LB is 144, as was given in the first problem. Okay? So therefore, d over dB squared is equal to 144. So to get the ratio of dA to dB, I'm just going to square root both sides, and now I know that the distance of A divided by the distance of B is 12, or in other words, A is 12 times further than B. And there's the answer to the second question. The last question here, a third star, a distance of 15 light years from Earth, has an apparent brightness of 6.4 times 10 to the negative 8 watts per meter squared. Find its luminosity. All right, this one I'm going to let you do. You should be recognizing that I'm going to use the brightness equals luminosity over 4 pi d squared. Please remember to put distance into meters. Apparent brightness is given. That should allow us to then find the luminosity, and we could find the wavelength and temperature and all those other things if we wanted from that. But go ahead, find the luminosity. Okay, hopefully you get something close to 1.6 times 10 to the 28th. All right, go ahead and see if you can find that. All right, that should be watts. Okay, all right, that's it for this video. Go ahead and try some problems.